All right, in this video, I want to get back to the idea of matter out there in space. And what we can do is we can, and I'm doing this to talk about the critical density, which you remember determines what kind of universe we live in if you divide the observed by the critical density. So if we look out into space and we count the number of stars in a galaxy, I mean, our galaxy may have as many as 1 trillion stars in it. It's a rather large galaxy. But most galaxies have at least 100 billion stars in them. So 100 billion stars, and it looks like there are about 100 billion galaxies out there. So 100 billion seems to be the magic number in our universe. And if we take those numbers and we estimate how much matter we get from that, we can come to an observed density of the universe. And it turns out that that density is less than a percent, less than a few percent, I should say, or less than a few tenths of a percent of the critical density. And so we are so far away from having enough matter in the universe, it's not even funny. That is to either have a flat universe or have a curved universe. Looks at this point, based on that our universe is going to go and expand forever. So only a few tenths of a percent of the necessary matter, but it turns out that there's some things out there that we hadn't considered, and I want to make that the key subject of this video. We're missing some things, to say the least, and this was discovered in the 1980s. This is a spectacular picture of a galaxy, and what astronomers can do is they can pinpoint different areas of the galaxy, and they can say, okay, how fast is a star moving there? And they can do a Doppler shift, and then go over to another spot, and they can measure a star there, and they can see, hey, how fast is this moving? So we can determine how fast the stars are going around the center of this galaxy. And then you can determine where the most of the mass is in the galaxy, which is pretty clear here. It looks like most of the mass is in the center. We'll talk more about this later, but in most of these galaxies there's a big black hole in the center of all that mass, and that's what's sucking the mass to the center of the galaxies, or I should say as the result of a lot of mass being there. That'll become clearer later on. I don't want to get into the details of that now. But the point is that the amount of matter there in the center of the galaxies, we thought in the 1980s, probably determines how fast the star, or not probably, but determines how fast the stars revolve around the center of the galaxy. Let's go back to Newton now and talk a little bit, and Kepler too, talk a little bit about how gravity behaves in our solar system. If we're a planet and we're very close to the sun, then Mercury, for example, has to go very, very fast to keep from being sucked in by the sun. And remember that the gravity is inversely proportional to the square of the distance. So those planets closest to the sun have to move much faster than the planets farther out. So as you go away from the sun, the planets are moving slower than the ones closer in, and that is just right out of Newton's handbook, so to speak. So we would expect then in a galaxy that most of the mass in the center of the galaxy, that we would see the same thing with stars. Now let's take a look at this video, and you can see where we have something like I don't care what you call it, a planet or revolving around the sun, or maybe a star going around the galaxy, and yet it has two components to it, and you know this from gravity. There's a velocity, and that velocity of the planet or star wants to take it and shoot it off into space. And then there's an acceleration due to gravity, which wants to drag that planet or star into the center. And they're competing with each other, and they're in equilibrium if the planet or star is revolving around the sun or the center of the galaxy. And if you speed up or you increase the velocity, then the planet or star can escape and go off into space. But if you slow the velocity down, then you get the star being sucked into the center of the galaxy, the center of the sun. And Vera Rubin started measuring galaxies I think around the 1980s, and along with colleagues, and wow, they found out that stars weren't behaving the way they should be. Most of the mass being in the center, we should see what we do in our solar system, that the stars will get slower the farther away you are from the center of the galaxy. But it turns out that the star speed remains fairly constant as you move away from the center of the galaxy. Well, that's crazy. It goes against everything we know and understand in physics. I mean, people during the 19th century, they were talking about, wow, maybe the laws of physics are wrong. Maybe we got something wrong along the way. Well, of course, they don't think that, but I think people were wondering what the heck was going on, that's for sure. And we've come to realize that there is matter, and we have no idea what it is. Now physicists very cleverly came up with the name dark matter. I'm joking about clever there, but they termed this matter, dark matter, because we have no idea well, we have an idea of what it is. We're probably, based on some of the things that we see in space, it's called weakly interacting massive particles, a clever way of coming up with WIMP, I guess. So we would expect them to be weakly interacting with other particles, but massive compared to other particles. And it looks like they're surrounding these galaxies. That's the only way we can explain the speed at which stars go around the center of the galaxy. So we've got this mass, and we have no idea what it is. And we've been searching for it for decades. There are experiments going on in many laboratories all over the world trying to discover what dark matter is. Because I tell you, the person that discovers that probably going to win a Nobel Prize. So people are very, very interested in this. And just think, we have a mass out there in our galaxy, and we have no idea what that mass is. Now, I'll show you another example of dark matter, but when we go and we add up the dark matter, we still don't have enough matter in our universe to keep it from expanding. So right now, even though it appears like the universe is very close to flat, we still can't figure, or we can't get enough mass in our universe to get it to collapse or even to have a flat universe. So the big question then becomes, why don't we have enough mass? The universe looks flat. Well, some other things tell us that the universe is very, very close to flat. It looks like it is flat. So why do we have this not enough matter in our universe? Well, we're going to talk about that in later videos. It's called dark energy, and I'll have a lot to say about dark energy later on, which won some folks a Nobel Prize in 2013. Now, I do want to tell you one other thing about this dark matter. It's not just been discovered by stars circulating around the middle of galaxies. It's also been discovered by gravitational lenses. And we've talked about gravitational lensing before. This was the case where Eddington proposed to test general relativity by going and watching an eclipse. And you may even remember this diagram. If you have a star behind our sun is going to, because of its gravity, it's going to deflect the light ray towards us, and it's going to make it look like there are two positions for that star in this flat diagram that we have, instead of the actual position where the star really is. But I also want you to think of this as in 360 degrees coming out of and going into the diagram, because we would have basically infinite number of apparent positions in a circle, because think about this, the light rays are coming off in all different directions, and they're going to come out of the page and then be deflected back towards the Earth, so it'll make it look circular, and this is called a gravitational lens. And by golly, look at this picture up here. We've got two galaxies, and then there must be at least one object behind those galaxies which causing a gravitational lens. And in fact, I suspect there are three objects behind there, because we have three gravitational lenses there. So why am I telling you about gravitational lenses? Well, I'm telling you about gravitational lenses because we can see how much the matter affects the lensing, and tell how much matter is there in those galaxies. And it turns out that if we just calculate the matter from all of the material we see, it's not enough. The gravitational lensing demands that there must be dark matter in those cluster of galaxies in order to explain this gravitational lensing that you see there, and in every other cluster of galaxies. So it turns out that we only have, what, about 20% of the mass needed to create a flat universe, and yet the universe looks flat by other measurements. So we're going to have to explain that in later videos when we start talking about dark energy.